According to previous derivation, we know that if you want to obtain the diffraction amplitude u function at any point of z, you can perform the following integral. Where the capital U0 here is the Fourier transform of the initial amplitude U0. And in previous slide, we have known that this term, capital U0, is the Fourier transform of the initial amplitude U0. So take the expression into here. Here, this integral represents the Fourier transform of the initial amplitude, and this is the capital U0. And in the total integral, we have two sets of parameters. One is x0, y0, the other is kx and ky. Then let us rearrange this integral. In this step, we just exchanged the parameters here. We first perform the integral with respect to kx and ky. After we finish this integral, we then perform the integral with respect to x0 and y0. Okay? And clearly, you see that the first integral here is a function of kx and ky. And we can express the first integral as a h function, which is of h of x minus x0 and y minus y0. What I am saying is that this integral can be written as a h function with the parameters x minus x0, y minus y0. So, by this definition shown here, the above integral can be simplified in the following form. So I shall correct here with one more parameter z. Okay? So, as the first integral shown here is represented by the h function, the total equation can be rewritten in this way. And you can see, for the first term, you have parameters x0, y0, and for the second term, you have parameters x minus x0, y minus y0. In mathematical in engineering and mathematics, we have learned that the above equation is the convolution of the u0 function and the h function. So the above integral can be written as the convolution of u function and the h function. Okay, so what I am talking is that if you want to obtain the amplitude function at any point of z, you can just perform the convolution with the initial amplitude, the convolution of the initial amplitude and the h function. Okay, let me say it again. What we want to know is that at the z is 0, at the initial point, we have known the initial amplitude u0. Okay, and what we want to know is the amplitude function at any point of z. This is what we want to obtain. How to find out this value? According to this result, we know that this value can be obtained by perform the convolution of u0 function with the h function. u0 here is the initial amplitude you should know, and the h is defined as this. So the total differential problem just like a system. The characteristic function of the system is the h function. For any input u0, you can obtain the corresponding diffraction field as u, which is the convolution of u0 and the h function. Okay, this is a very important result in this chapter. If you want to know the diffraction field at any point of z, you can just perform the convolution of the initial amplitude with the h function. However, as I have said, the h function is defined as the integral shown here, but this integral is too complicated. We have to simplify the process to find out the value of the amplitude function at any point of z. How to simplify the expression of the h function? Let me explain it. We know that the h function can be written in the following form. To simplify it, we first consider the integral with respect to kx. We first multiply the integral with a term shown here. To cancel the effect of this term, we have divided it in the integral. So inside the integral, you will have the following term. Okay, as I have said, if you multiply the integral with this term, then you have to divide it here to cancel the corresponding effect. And as you have the form in the integral shown here, it can be arranged as that. As we know, the z divided by 2k times kx squared minus kss plus kx squared divided by 2z. This one can be arranged in the following form. It can be rearranged as this one. So we can replace the order here by this one. Okay, and then we define another parameter c. We let the square of c to be minus jz over k times k sub s minus k over z times x squared. If the square of c is defined as this way, it can be rewritten as z over jk times the following term. Okay, then according to the definition of the square of c, you can then obtain that the c can be expressed as the following equation. As a result, dc can be written as square root of z over jk times dks. So according to this relationship, we can know that the dkx can be written as square root of jk over z times dc. So by this relationship we have obtained, let us replace this one by this one. So let's do it. According to this relationship shown here, the above integral can then be written in the following way. Okay? And if you are very familiar with the integral equation, you will know that this integral will be equal to the square root of 2 pi. So the result will be square root of 2 pi times the following terms. Okay, so we finally obtain the result for this integral. So similarly, you can also obtain the result for the integral with respect to ky, which is square root of 2 pi times the following terms. According to the result for this integral and this integral, we then can rewrite the h function. Then let us rearrange these terms, and you will obtain that the h function is the inverse of 2 pi times jk over z times exponential minus j k over 2z times x squared plus y squared. Then, by using k is 2 pi over lambda into here, then the above h function can be written as the following way. As you can see, initially the h is expressed in a very complicated form, but now we finally obtain the h function in a simple form shown here. So it will be easy for you to perform the convolution. If you want to know the amplitude function at any point of z, then you can just perform the convolution of the initial amplitude with the h function. Okay, and this means that you just perform the following integral. Okay, let me summarize the process here. If at the z is 0, at the initial point, you have known the initial amplitude u0. Then you want to know the amplitude function at any point of z. The amplitude function at any point of z is u of x, y, z. How to obtain this value? The amplitude at any point of z can then be obtained by perform the convolution of u0 with the h function. And the detailed process is to perform this integral shown here. Okay?